All right, let's talk about quantum physics. I know, it's got this reputation for being, well, impossible to understand. But stick with me, because today we're going to pull back the curtain and demystify this whole thing, from the stuff that seems spooky all the way to the truly spectacular. Let's do this. So, our story really kicks off with a great line from Albert Einstein himself: spooky action at a distance. Now, get this. He was talking about something called entanglement. This idea that two tiny particles could be linked in this mysterious way, no matter how much space you put between them. Even Einstein, the guy who reshaped physics, thought this was just too weird. And that spooky idea? That's exactly what we're going to unpack today. Okay, first things first, let's get one thing straight. When we talk about quantum teleportation, you've got to forget all about Star Trek. This isn't beam me up, Scotty. We're not sending people or objects across the galaxy. What we're actually talking about is transmitting information. It's about sending the perfect, exact quantum state of a particle from one place to another. And here's the kicker. The original particle state gets destroyed in the process. So yeah, it's way more like a perfect, instantaneous quantum fax machine than a teleporter.
So, to really get a handle on all these huge ideas, we've got to start small. I mean, really small. We need to meet the fundamental building block of quantum information. Let's meet the star of our show, the qubit.
You know how in your computer everything boils down to bits, right? A bit is just a 0 or a 1, on or off, super simple. Well, a qubit is the quantum version, and it totally throws that rulebook out the window. A qubit can be a 0, it can be a 1, or, and this is where it gets really wild, it can be a mix of both 0 and 1 at the exact same time. It's this bizarre, mind-bending state called superposition. So how in the world do you even picture that? Well, this state circle here is actually a pretty neat way to do it. Just think of it like this. The 0 state is that horizontal line, and the 1 state is the vertical one. A qubit, it can exist anywhere on that circle, representing some unique mix of both 0 and 1. It's a really handy way to get your head around this idea of superposition. And here's the cool part. We can actually control these qubits using things called quantum gates. The X gate, that's the simple one. It just flips a 0 to a 1 or a 1 to a 0. It's basically a quantum light switch. But the H gate? Now that is where the magic happens. The H gate takes a plain old 0 or 1 and smashes it into a perfect superposition of both states at once. This one little gate is the key to pretty much all the power of quantum computing. Okay, so a qubit can be two things at once. What's the big deal, right? Well, let me show you. We're going to see what this superpower can do in a simple little game. First, let's look at the normal version with a regular penny. Alice puts the penny down, heads or tails. Then Bob can choose to flip it or not. Then Alice gets one last turn to flip it or not. Pretty straightforward, right? It's a total game of chance. 50-50. Totally fair, but totally random. But what if Alice decides to play with quantum rules? What happens if she ditches the penny and pulls out a single qubit instead? This is where the game gets interesting. Check this out. This is Alice's secret weapon. She starts by hitting her qubit with an H gate, putting it into that both-at-once superposition state. Now, Bob takes his turn. He can flip it or not. It literally does not matter what he does. Because after he's done, Alice just hits it with a second H gate, and poof, the weirdness collapses, and the math of quantum mechanics forces the qubit to land on 0 every single time. She's not leaving it to chance, she is guaranteeing a win. Okay, so that's what the math says should happen. But what happens when you try this on an actual, real-life quantum computer? Well, we did just that. We ran this game a little over 1,000 times. And look at the results. It's not a perfect sweep for Alice, so what gives? You can see it right here in the data. Alice absolutely crushed it. She won most of the time, but Bob still snuck in some wins. And this little imperfection points to one of the gnarliest challenges in quantum computing today, something called noise. These quantum states are incredibly fragile. The tiniest vibration, a stray bit of heat, it can mess things up and cause an error, flipping the results. Figuring out how to protect qubits from this noise is one of the biggest jobs for quantum engineers right now. All right, so we've seen the weirdness of one qubit. Now, let's level up. What happens when you take two qubits and link their fates together? Well, my friends, this brings us right back to that spooky action that had Einstein so puzzled: entanglement. So, yeah, let's just cut to the chase. What exactly is this spooky entanglement thing? Okay, when you boil it all down, entanglement is really just about connection. It means two things are no longer independent.
I love this analogy from physicist Frank Wilczek. Imagine you have two cakes. If they're independent, finding out the first one is square tells you zip about the second one. It could be square, it could be circle, who knows. But if those cakes are entangled, well, now their fates are linked. If the first one's square, you know for 100% fact the second one is square too. No question.
And that's the core of quantum entanglement. You have two or more particles that are linked up, and their states are no longer separate, no matter how much distance you put between them. The pair of shoes analogy is probably the best one I've heard. Imagine you have a pair of shoes, and you put each one in a separate box and mail them to opposite ends of the earth. The moment you open your box and see a left shoe, you know instantly that the other box contains a right shoe. That knowledge is instantaneous, faster than light. That's entanglement. Okay, so this is all very weird and cool, but what can you actually do with it? Well, how about we use this spooky connection to build something truly powerful, a form of communication that is physically impossible to hack? Here's a quick and dirty version of how quantum cryptography works. So Alice sends Bob a stream of photons, little particles of light, that stand for zeros and ones. Now, because of the weird rules of quantum measurement, Bob can't actually detect all of them successfully. He only gets a fraction. The cool part is what happens next. They just hop on a regular open phone line and say, hey, which ones did you get? Oh, I got number 3, 7, 12, and 21. The specific values of those photons they both agree were received, that becomes their secret key. So why is this so secure? Why is it unbreakable? Because its security isn't based on a hard math problem. It's guaranteed by a fundamental law of physics. See, in the quantum world, you can't look at something without changing it. The very act of measuring a quantum state disturbs it. So if some eavesdropper, let's call her Eve, tries to sneak a peek at the photons as they fly by, her measurement will leave a trail of errors. When Alice and Bob check their key and see those errors, the alarm bells go off. They know someone was listening in, so they just throw that key away and start over. It's like a self-destructing message. The takeaway here is that none of this is just head-in-the-clouds theory anymore. These ideas, superposition, entanglement, they are the blueprints for technologies that are going to fundamentally change our world. So let's circle all the way back to teleportation. Now that we get what entanglement is, it makes more sense, right? It's not about moving atoms around. It's about using one of those linked, entangled particles to transmit the perfect quantum state of another particle from point A to point B. You're teleporting the information, the very identity of the particle, not the particle itself. And again, this is not sci-fi. This is happening right now. Look at this progress. Back in 1997, scientists teleported the state of a single photon for the first time. Just a few years later, in 2004, they did it between atoms, and by 2015, they were teleporting quantum information over more than 100 kilometers of fiber optic cable. I mean, the pace of progress here is just breathtaking. So where does all this lead? What's the end game? We're talking about a future that is literally built on entanglement. Just imagine it, a quantum internet connecting computers that are more powerful than anything we can dream of today. Quantum sensors so precise they could change medicine forever. And of course, global communication networks that are, by their very nature, completely and totally secure. And it all stems from these bizarre, spooky quantum rules we've been talking about. So we've gone from Einstein thinking this stuff was just too spooky to be real, all the way to us building actual devices that use these spooky rules as their operating manual. It really makes you wonder, right? Now that we're starting to get the hang of controlling this strange and powerful quantum world, what's next? What other things that seem like pure science fiction today are going to be our everyday reality tomorrow?